Hello, my name is jaideep. I am from first year CSE and my topic is System Effectiveness Evaluation using star and delta transformations. Introduction. Generally, the reliability graphs of power systems, communication systems, data processing system, etc. are complex and have large number of maintainable bidirectional elements. For a terminal pair system, effectiveness evaluation is assumed available. The steady state availability for repairable systems is analog to the probability of success for system with non-repairable elements. Steady state availability is the proportion of time the system remains in operating state when the time interval considered is very large. Many times, in addition to evaluation, steady state availability, it is necessary to evaluate system frequently of failure, mean uptime, mean downtime, etc. Series parallel reduction also is not sufficient for complex systems. Delta star or star delta transformation is required to reduce the network. All equations apply to general reliability diagrams with imperfect nodes and branches. In general, the star-delta transformation requires solving three nonlinear algebraic equations. An iterative procedure to solve these equations is presented. The accuracy of the present method is compared with the other methods by numerical examples. Next is nomenclature. Ij subscripts which denotes a node I or a branch between nodes I and J. P a grade Q at the rate is probability of success or failure of elements a grade comma a grade is equals to ij and at the rate comma dollar at the rate comma r at the rate is failure rate, repair hazard rate, mean repair time of element at the rate. Set of I similar to J is nothing but even is success of the subnetwork between nodes I and J, and of E is steady state failure rate of the event E. Next is assumptions. The following assumptions have been made in this slide. The reliability graph of the system exists, is undirected and contains no contradictions. Each element, a node or a branch, and the system is either good, operating, or bad. That means failed. All elements can be maintained. The states of all elements are S-independent. This means that the failure or repair of one element does not affect the failure or repair of other element. So they are telling that all the elements can be maintained. The states of the element are of S-independent. It means that the failure or repair of one element does not affect the failure or repair of another element. All elements are operating when they are good. Example, no cold standby or switched redundancy is used. Times to failure and repair of each element are exponentially distributed as transition rates are constant. the system is in steady state. For the elements of transformed network, the fourth and the sixth assumptions do not hold true. The elements of the transformed subnetwork are mutually independent. The distributions of failure and repair time do not remain exponential after transformation. However, for simplifying the analysis, it is assumed that these assumptions are valid for the elements of the transformed network also. Next, transformations, non-repaired elements. The transformations derived by Banerjee and Rajamani were claimed to be extract. However, Singh and Kankam pointed out that these transformations are approximately only. Rosenthal, while defining the equivalence of two networks, mentioned the requirement of preserving point-to-point connection probabilities for all pair of points in the original network for the exact delta star transformation. The controversy about the exactness of the transformations arose due to lack of definition for the equivalence of two sub-equivalence networks. A transformation which is exact consideration certain aspects of the equivalence may turn out to be the approximate when some additional features of the equivalence are considered. For example, transformations suggested in two subnetworks. These transformations become approximate when preservation of point-to-point connections probabilities is considered for the equivalence. Rosenthal and Frick derived equations for transforming any general three-terminal network into a star network by assigning a non-zero failure probability to the star node, thus preserving probability 5 especially defined classes of states for star delta networks as shown in the figure 1. The transformation applies to a subnetwork with perfect nodes and permits inclusion of only to those imperfect nodes which are incident to one external edge. Also, repair is not considered in the transformation. Rothenthal as well as Gupta and Sharma suggested delta star transformation without including the imperfect star node when the reliability network has the property. Each ST part which includes edge of S enters S as I. For this special case, they mentioned the efficiency of preserving probabilities of events I, I to K and I similar to J belongs to I to K for the transformations. However, this is no mention of the way to assure that a given network has this property. Moreover, many networks do not have this property. For example, the network figure 3 has two deltas with node set 2, 4, 5 and 3, 5, 6. The network has 10 paths for a terminal pair S to T. Amongst the nodes of the two sets, Not a single node is such that every S2T path, which includes the edges of S1 or S2, enters only at a particular node. This restricts the applicability of suggested transformations. In addition, for a delta network with identical values of branch reliability, the transformations yield unequal reliability values for star branches, which is unreasonable. Next is repaired elements. For series and parallel systems, expressions for failure rate and for repair time under steady star of equivalent single element are derived in 19. System states are obtained under Markov model. The probability of the system being up is equated for series system to derive the expression of repair time of the equivalent element. In parallel system, the probability of the system being down is equated to derive the expression of failure rate of the equivalent element. For delta star or star delta transformations, in addition to above mentioned 6 probabilities, equations for 6 failure W of I to j, comma, W of j to k, comma, W of k to I, comma, W of I to j belongs to j to k are derived in the supplement. These equations are derived using network approach, that is, using series parallel combination rules and using expressions of an equivalent element for series and parallel systems as given in figure 19. For delta star transformation, the three equations obtained by equating last three failure rates for the two subnetworks are combined to form one equation. Transformed subnetwork. The elements of the transformed subnetwork are S independent. When the elements are considered S independent, S dependent, the analysis would be tedious, rigorous, and to keep track of the degree of S dependent would be very difficult for large networks. To simplify the analysis and to avoid the difficulty, the transformations equations are derived assuming S independent elements. In the star delta transformation, probabilities of all compound events are not matched. The error involved as a result of approximation is inequivalence would propagate in all further calculations. Applications. Both star delta and delta star transformations allow us to convert one type of circuit connection into another type in order for us to easily analyze the circuit. These transformations techniques can be used to good effect for either star of delta circuits containing resistance and impedances. Usually, star connection is used in both transmission and distribution networks with either single phase supply or three phase. Delta connection is generally is used in distribution networks. Since insulation required is less, star connection can be used for long distances. So both star delta and delta star transformation will allow us to convert one type of the circuit connection into another type for easily analyze the circuit. Conclusion: star delta starters are probably the common reduced voltage starters. They are used in an attempt to reduce the start current applied to the motor during start as a means of reducing the disturbances and interference on the electrical supply. So, star delta starters are probably the most common reduced voltage starters. They are used to attempt to reduce the start current applied to the motor during start as to the as the means to reduce the disturbances and any problems or interferences on the electrical supply. So I thank the faculty and the college for giving me opportunity to tell the topic in this module.